Hello students, welcome to Abstract Algebra. Let's begin Lesson 1. Lesson 1 begins with a fitting question. What is algebra? That is the topic for Lesson 1, Section 1 and Subsection 1.1. What is algebra? Have you thought about that? We had been studying algebra for a long time, from way back from elementary school days. But then again, what exactly is it about? In the simplest terms, algebra is a study of operations. Here, we're talking about mathematical operations, of course, not military operations or medical operations or any other operation you can find from the dictionary. It must be mathematical operations, or equivalently, algebraic operation, or just operations. They're all the same in mathematical realm. Now, what is an operation in that case? We can define it like this. It's a multivariable function defined on one or more non-empty sets with a set of some special properties which we call the algebraic structure. So basically that's it. We study algebraic operations and their properties which we call algebraic structure. Algebraic operation and algebraic structure, those are the kind of things that we have to study, and their applications, of course. Some of them are exemplified here, but we're going to come back and discuss those after getting through some operations, especially for the easiest case. And let's begin. The simplest type is internal binary operations, and it's defined like this, as a double variable function in S. That's the most ideal case, but in some case, not everything can be defined, so we may have to restrict the domain a little bit. Here's some examples. Okay. Real number arithmetic, addition, and multiplication. They both fall into this category. Any pair of real numbers, A, B, we can define sum and product uniquely, right? Now, do they have to be all numbers? Not really. How about some polynomial addition and polynomial multiplication? By the way, this notation here, R bracket open x, that means the set of all polynomials with variable x with integer coefficient. Excuse me, did I say integer coefficient? Real coefficient, excuse me. Real coefficient. Of course, we can consider integer coefficients too, but in that case, it should be zx. Polynomials with rational coefficients, qx, and complex coefficients, cx. But in case of complex, traditionally we use character z, so cz is typical expression, it's traditional. Otherwise, we use x most of the time. Of course, we can use other characters if you prefer. And speaking of other numbers, yes, we can consider numerical addition and multiplications for other number systems too. Natural numbers, whole numbers, integers, rational numbers, complex numbers, those kind of things. Here's another example, matrix addition and matrix multiplication. And if you're familiar with linear algebra, you'll recall that matrix addition is valid for any matrices of the same size, n by n. Matrix multiplication, that's a little bit different, so I restricted myself to square matrices only, n by n. Here's another example. Way back from college algebra days, we went through compositions. What is this script f(x)(x)? That's a set of all functions from x to x. So from there, we select a couple of functions, f and g. They both go from x to x, and we take the composition that also starts from x and ends up at x. So we end up with an internal binary operation. We can, of course, create some artificial examples like these, or anything actually, but whether that's interesting or meaningful, that's besides the point. We can always create one. Those are the simplest type, and let's consider some less obvious type, kind of like this, division. In that case, the denominator should be non-zero, so we need some restriction. So not everything in S cross S will do. Not everything from R cross R. So we have to consider this Rx notation, this notation here, which means non-zero real numbers. Same for polynomial division, Rx, this cross notation, that means non-zero polynomials. Of course, if you want to change the number system, you can go ahead and do that. Integer coefficient, rational coefficient, complex coefficient, all those kind of things. Here's another example, real exponential. In that case, the base A has to be strictly positive. So instead of Rx or R cross, I use R plus here. Positive real numbers only. For complex exponential, A, the base has to be non-zero complex numbers. But I don't know if anybody is comfortable with this notation. I don't think we're going to do this in this class, so let's move on. Here's some more on compositions, but not just composition, but composing inverse function. And f inverse must exist, so we have to restrict my domain into the set of bijections. One-to-one onto map, so f inverse exists. And this one is called conjugation. Again, f inverse must exist, so that should be selected from the space of all bijections, not just all functions from x to x. By the way, this inversion is not that important, but this one, conjugation, will show up a lot in this course. So please remember that. By the way, maybe it would have been better to restrict ourselves completely within the set of all bijections. Yeah, if we do it like that, then we can restrict, we no longer have to restrict ourselves, so it falls into this. But sometimes we can do that, most of the times, but not always, as a matter of fact. Okay, we have some further examples here, and those are for the student who went through number theory already. Div operation and mod operation, do you remember those? Division algorithm here, and then taking the quotient q, that's the div operation, and taking the remainder, that's mod operation. Remember those? So here's some example. Mod 17.5, let's see. Does it support div operation? No, it doesn't. Oh, quotient, okay. So div operation can be done by quotient 7,5. That's Mathematicus language. And mod operation by mod. No div, because div is taken by divergence. Similarly, we can do the same thing for polynomials. Quotient operation and remainder operation. In the division algorithm, taking the quotient is polynomial quotient operation. Taking the remainder is polynomial remainder operation. Here's some examples. F is this quintic and G is this cubic polynomial. And then polynomial quotient, F divided by G, will turn out to be this. And polynomial remainder will turn out to be that. In number theory, we did these, and we're going to extend this into polynomials in this course. It's going to be a topic for the latter 1/3 of the course, and that's something we are going to do probably in week 13 or week 14 there. Another operation that you may have to remember from number theory is GCD operation, and we can do the same thing or similar thing for polynomials as well. The greatest common divisor of polynomials. Again, that's something we are going to do way later. But We're going to cover those in this course. Before moving on to the next topic, let's discuss something further about some remarks and terminologies, especially terminologies. Let's come back to this definition here. This definition includes two aspects, which I specified here. The domain is D and the target is S. Let's look at the domain first. So, what is the feature of a function? Do you remember? A function is a relation where one element of domain must be assigned to one and only one from the target, right? That's the function. That means one element a comma b from domain is assigned one and only one function value a star b. So this a star b exists uniquely for all a comma b in the domain. So if I select this pair from the domain, then the operation has an answer, and the answer is unique, a star b. In this case, we say a star b is defined. Otherwise, it is not defined or undefined. That happens when a comma b is selected outside of the domain, such as in this kind of situation, if the denominator is 0, then numerical division is undefined. Now let's look at the second concept here, the target. Target is S means the end result, the function value a star b, belongs to S again. So if you take this operation a star b and the answer a star b belongs to S again, that's what this target is telling us. And we say S is closed under that operation. That means the target is S. I think we had been using this term, closed under addition, closed under subtraction, these kind of things, way back from elementary school days. And we know that the addition is closed under set of integers. Oh, I said it backward, excuse me. Set of integers is closed under addition. Set of natural numbers is closed under addition, but not closed under subtraction, those kind of things. Set of integers is closed under addition, but not closed under division, those kind of things. Finally, putting these two together, we say the operation is well defined. So well defined means the domain and target, both of them. And whether there's some exceptional element which is undefined does not mean the entire operation is undefined. We can always restrict our domain a little bit. But of course, in some case, when that restriction is too inconvenient, then we have to think some other fashion. Anyway, those are the terms that you'll have to remember. Closed under blah, blah, blah. Defined, undefined, those kind of things. Now, do we have enough time for external binary operations? Maybe, but I'd rather stop here and resume in a second video. Stay tuned.